So here we have our pendulum. We can see the L of the string, the angle it's making with the axis, and then the weight of the pendulum, and then the amplitude that it's swinging at. So using the small angle approximation, we know that sine theta is equivalent to theta and tan theta is equivalent to theta. So we know that force is equal to mass times acceleration, and using this, we can see that force would be equal to the weight, or the mass times gravity sine. And using small angle approximation, that gets us to force equals mg theta. Our past knowledge of pendulums gives us the equation acceleration equals negative omega squared times the amplitude. So we can manipulate our force equation to be acceleration equals force over mass. We can then manipulate it further by putting mg mg theta where force is, canceling our masses and leaving us with g theta. So our acceleration times the angle. And then using that gives us our acceleration. And using this equation, we know that g theta is equal to negative omega squared times the amplitude. Looking at this, we can see in our triangle that amplitude over L is sine theta. So theta is equal to amplitude over L, or the length of the pendulum. So using that, G at amplitude over L equals negative omega squared amplitude. So we have two amplitudes cross. So we know that G over L is equal to omega squared. And we previously know that omega is 2 pi over the period. So if we implement this to here, we have G over L equals 4 pi squared, because we have to use that square and distribute, over the period squared. So using algebra and manipulating this further, we have that squared. We have period squared equals 4 pi squared times L over G. So we need to get rid of the square root, so we take the square root of both sides. We have the period is equal to 2 pi times the square root of L over G. So this equation shows us that the only thing that affects the pendulum's period is length, because gravity stays the same and 2 pi is a constant. And earlier we got rid of mass very early in the derivation. So the only thing that affects, or should affect, a pendulum is the length of the string.
Alright, so since Joe derived this beautiful equation, we wanted to go out into the real world and empirically test this equation for ourselves. So what we did is we went and got my hammock. It's a naturally occurring pendulum, put it between two trees, and we wanted to test if mass really did affect the period of the hammock, because naturally it kind of seems like it might. And so we tested the hammock at different lengths, different masses, and Megan can talk a little bit about what we found out.
So we looked at a certain length, we tested the period at two different masses, and we found that they're very similar. We have 1.69 seconds and 1.70. And when you look at each length, these are all the three lengths we tested, the period between the two masses is very, very similar. There is a little bit of error where there's expected uncertainty. We're dropping the hammock. There's always the possibility that it was dropped slightly different, that there was wind, that there's lots of variables that could have affected that a little bit, so we expect this uncertainty, but there's not that much difference. So our data does suggest that it does support this theory and this equation, because we should see with the acceleration of gravity being constant and this being constant, the only thing that should affect the period is the length, and that's what we found from our data.
Yeah, and so as you increase your length, your period also increases. And mass, again, no bearing.